Howdy, folks. Today we are going to be discussing Newton's second law of motion. And what you're seeing here is an example of Newton's second law of motion in action. And so, what's going to be important in Newton's second law with what we're looking at here is the fact that we have this car and it is moving, and then it all of a sudden comes to a stop as it runs into this object. And so that car is experiencing acceleration. It just so happens that the acceleration is in the opposite direction that it is currently moving, which causes it to come to a stop. So with that acceleration and the mass of the car, those two components are going to result in the force that the car experiences, which is why you see that damage happen. So let's go ahead and learn a little bit about that today. All right, our learning target for today is I can describe Newton's second law of motion and use it to calculate force. I want you to go ahead and set up your notes. Our topic for today is Newton's second law, and our essential question is what is the relationship between force, mass, and acceleration? All right, folks, go ahead and pause this lecture video and go and check out this silly little video I posted in the Nearpod. It's a little interesting. It's just kind of goofy, but it does kind of help explain what it is we're going to be talking about with Newton's law. All right, so let's go ahead and start off by defining Newton's law. The force required to accelerate an object increases as the mass increases and vice versa. All right, so what exactly does this mean? Well, we have this kid here, and this kid is pushing with all of his strength. And so he pushes with a certain amount of force. So in both situations, the kid is pushing with the same amount of force. And when he pushes on the car doesn't accelerate very much. It accelerates slowly because it has a very high mass. And so the kid pushes, but it only accelerates a little bit. If the kid pushes with the same force on this lawnmower, the lawnmower has much lower mass than the car, so the lawnmower is going to accelerate a lot more, and he's going to get the lawnmower going a lot faster, a lot quicker. So that's basically what we're saying. If you have two objects and you put the same amount of force on them, if whichever object has more mass will accelerate less, and whichever object has less mass will accelerate more. What question does the previous slide answer? All right, so we can actually put all of that into a mathematical equation. And what that equation states is force equals mass times acceleration. So basically what we are saying here, what we talked about is the force that we put on an object is inversely related to the mass of, I'm sorry, the acceleration is inversely related to the mass of the object. So if we were to rearrange this equation and put the mass divided, or do the force divided by the mass to equal the acceleration, you would see that as the mass increases, the acceleration decreases. But this is the typical way of looking at it, F equals ma. And so the other way to think about this is as the mass increases and the acceleration increases, so does the force. So it just depends on how you're doing it. So what are the units involved here? Well, mass we measure typically in kilograms. And acceleration, you'll remember when we learned about that, we measured in meters per second squared. So when we combine kilograms and meters per second squared, we get a unit kilogram meters per second squared. We can simplify that unit to be a Newton, which is what we have talked already about measuring force in. So a Newton is kilogram meters per second squared. All right, so let's go ahead and do a practice problem together. This is on page 19 of your packet, problem number 1. How much force is needed to accelerate a 68 kilogram skier at a rate of 1.2 meters per second squared? All right, so let's pull the information out of this problem that we have. And we have the mass of the skier is 68 kilograms. The acceleration of the skier is 1.2 meters per second squared. So we are solving for F, and we know that F equals ma, force equals mass times acceleration. So we go ahead and plug in the information we have. 68 kilograms times 1.2 meters per second squared. So it's right there. You do the math, 68 times 1.2 is 81.6. When you combine the units, you get kilogram meters per second squared, but we know because we're dealing with force that that unit simplifies to newtons. So our answer is 81.6 newtons. Now, please be very, very clear on this. When you enter your answer into Schoology, your unit needs to be the simplified unit. In this case, the simplest unit is going to be newtons, so you have to put in newtons. You cannot put in kilograms, meters per second squared. It needs to be newtons. So just please remember that. Also, quick note, if you wanted to use a formula triangle for this, you would have F on top and M and A on the bottom. So feel free to write that out for yourself if that helps you. What question do the previous slides answer? All right, so let's talk a quick difference between mass and weight. So mass, by definition, is the amount of matter in an object, and we learned about that last unit. And our standard unit for mass is going to be kilograms. So here's what you need to know about mass. Mass, basically a very oversimplified way of putting it, is mass measures the amount of atoms in an object, and the amount of atoms is the amount of matter. So no matter where you are in the universe, you are going to have the same amount of atoms in an object. Just moving it from place to place does not change the number of atoms, and therefore it doesn't change the amount of matter, and therefore it does not change the amount of mass. So right here, if on Earth we have a toy dog, or a little toy of a dog, it will have and it has a mass of 1 kilogram. If we move that toy dog to the moon, it will still have a mass of 1 kilogram. And this is because the amount of atoms, the amount of matter in the toy and the weight, or this metal piece here, has not changed. It's the same number of atoms, same number of matter, whether it's on the Earth or on the moon. Even if the gravity does change, the amount of mass does not. Weight, on the other hand, is very different. Weight is the force of gravity acting on an object. So, on Earth, the gravity has an acceleration of 9.8 meters per second squared. So, if we have a block that has a mass of 2 kilograms, so 2 kilograms tells us the amount of matter in the object, and we have this block with 2 kilograms of mass, on Earth, it will have a weight of 19.6 newtons. That's because we just learned force equals mass times acceleration. Well, the mass is 2 kilograms, and the acceleration of gravity is 9.8 meters per second squared. So if we multiply those two together, we get the force of gravity, or the weight. So on Earth, this 2 kilogram block would have a weight of 19.6 newtons. However, if we take that same block and we put it on the moon, where the weight, or where the gravity is much less than on Earth, it's about 1/6 of what it is on Earth, and we weighed that block has a weight of 3.3 newtons. Okay, it weighs 1/3 because the gravity is, or sorry, 1/6. The gravity is 1/6 of what it is on Earth. So same amount of matter. However, it weighs less. There is less downward force on it because the gravity of the moon is much less than that on Earth. Now, if you went to deep space where there is no gravity and you took that same 2 kilogram block, it would actually be weightless. It still has 2 kilograms of matter in it. However, there is no downward force acting on it, and therefore it has a weight of 0 because there is no gravity in outer space. So there is a difference between mass and weight. So I always like to take this as an opportunity to just kind of share this. I always like this little kind of motivational poster, but I know that a lot of people sometimes make a lot of judgments based off of what their scale says. You measure yourself on the bathroom scale, but here's something really, really important to note about a scale. The scale can only give you a numerical reflection of your relationship with gravity. That's it. It cannot measure beauty, talent, purpose, life force, possibility, strength, or love. So don't let yourself ever get tied up with what those numbers on a scale are, because literally all it is a mathematical equation that just tells you about your relationship with gravity. It does not tell you anything else about yourself. All right, so we've been talking about weight versus mass. So let's go ahead and relate this over to what we were talking about with force. So Force equals mass times acceleration. We've discussed the fact that weight is a force, so we can replace force with weight. And we've talked about how gravity is an acceleration, so we can go ahead and replace acceleration with gravity. And what we're going to get is a formula, weight equals mass times gravity, or W equals mg. The unit for this is going to be newtons. In America, we use pounds instead of newtons. But we are going to be measuring these things in newtons. Remember though, if you want to kind of give yourself some context, a newton, 1 newton is a quarter of a pound approximately. So what this means, if we have an astronaut here, and this astronaut has a mass of 120 kilograms, remember 120 kilograms tells us how much matter is in that astronaut. Their weight is going to be 120 times 9.8. In this example, we're rounded to 10, but I want you to be doing 9.8. And that tells us that this astronaut has a weight of 1,200 newtons on Earth. If that astronaut then went up to the moon, their mass is the same amount of matter. However, their weight is only going to be 200 newtons. So they are going to feel much lighter on the moon because the moon has about 1/6 the gravity of the Earth. All right, what question do the previous slides answer? All right, folks, let's do a couple practices first. All right, first thing, I want you to go ahead and answer this question. Is 35 kilograms a mass or a weight? Go ahead and answer the question on Nearpod. All right, 35 kilograms it tells us the amount of matter in an object, and so that is going to be a mass. And if you selected that answer, you've got the correct answer. All right, next up, I want you to try solving this problem. What is the weight of a 35 kilogram dog on Earth? I have thrown up a little formula triangle here for you to solve this problem. So I want you to go ahead and pause this video and try to solve that problem on your own, and then put your answer here. All right, let's go ahead and take a look. What is the weight of a 35 kilogram dog on Earth? The mass of the dog is 35 kilograms. Gravity on Earth is 9.8 meters per second squared. Weight equals mass times gravity. We have the mass at 35 kilograms, the gravity at 9.8 meters per second squared. 35 times 9.8 is 343. Kilograms times meters per second squared is a newton. So our answer is that dog has a 343 newton weight. Next one. What is the weight of the same 35 kilogram dog on the moon? The moon's gravity is 1.6 meters per second squared. Go ahead and pause this video, solve that problem, and then come back. All right. The weight of the same dog, well, the mass is 35 kilograms. The gravity on the moon is 1.6 meters per second squared. We use the same formula. We just replace gravity with 1.6 meters per second squared. 35 times 1.6 is 56, and the unit is newtons. All right, last one here. A lamp has a weight of 28 newtons on Earth. What is the mass of the lamp? Go ahead and use that formula triangle to solve that problem. All right, the weight of the lamp is 28 newtons. The gravity acceleration on Earth is 9.8 meters per second squared. The mass is going to be weight over gravity. So remember, we're solving for mass, so you cover that up, you get weight over gravity. The weight of the lamp is 28 newtons. The acceleration due to gravity is 9.8 meters per second squared. And so you do 28 divided by 9.8, and that gives you 2.9. And in these units, the meters per second squared cancels out with meters per second squared, and you're left with kilograms. So this W should be an M, but mass equals 2.9 kilograms. All right, in your packet, you will then, if you turn to this page, you will see some information about mass versus weight. I would highly recommend that you take a little bit of a moment to go through all of these and determine what is the similarities and difference between mass and weight. And I've included a Venn diagram here for you to organize your information. All right, down here you will see our formulas, and then you will see a bunch of practice problems. So that is what you're going to want to be doing to help you practice. All right, whole bunch of practice problems that are all very useful for you to do. Alrighty, folks. So on a scale, I guess in this time we got 1 to 3. So the question is, where are you at in terms of your understanding of this? So no clue. After practice, I will get it, or good to go. All right. So if you were, I don't understand it, I want you to go over to Schoology and watch the video tutorial. If you just need some practice or you're good to go, I want you to do some of that Newton's second law practice and check your answers on the key, which is provided on Schoology. As always, folks, if you have any questions, please feel free to reach out and ask.